This is section 17.4 and it's about titration of weak acids and weak bases, which for the most part they behave similarly to the strong acids and strong bases, but with some additional considerations. The first is that at the beginning of the titration the initial pH is higher, and the reason for that is that weak acids do not release as many protons as a strong acid. Therefore the concentration is going to be smaller and the pH is going to be higher. Okay. Another thing that to consider is that the weaker the acid, which means lower the Ka, you have even less protons released to the solution, and therefore you will have a higher initial pH. That means as the acid becomes weaker and weaker, then the starting pH in a titration will be higher and higher. Also, when you start adding the base, then you have an initial rise in pH, and the reason for that is because it's not until you reach the pKa value of the acid then the acid becomes resistant to changes in pH. Okay, so at the beginning most of the acid will be consumed and it will be producing the conjugate base, but the concentration of the conjugate base is so small that it's not starting to behave as a buffer. So you have that small jump at the beginning of the titration. Okay, and higher pKa values, again you have higher initial raises. So they will be higher pKa values mean the acid is weaker and therefore will be even less resistant to changes in pH when you start the titration. Now, the pH at the equivalence point for strong acids and bases, there is nothing to think about there. The pH is going to be 7, but when you are titrating a weak acid, at the equivalence point, what is going to control the pH is the conjugate base. Okay? At the equivalence point, the conjugate base controls the pH, and therefore it will behave as a base and it will end up changing the pH to basic pH. Okay, that's why at the equivalence point you are not at 7. If you are starting with acid, if you are titrating an acid, the pH at the equivalence point is going to be higher than 7. It would be basic pH. And if you remember from the titration curve with acids, strong acids and strong bases, there is an abrupt change in pH around the equivalence point. Well, when you have weak acids, then there is a smaller jump. We can see this abrupt change as a jump in pH when you are around the equivalence point. That jump is really high if you are with strong acids and bases, but the weaker the acid is, the smaller that jump is. So let's take a look at a figure in which that should become more clear. Okay, if you have a strong acid, then you have pretty much this jump in pH. This is for a strong acid. And if you have a weaker acid, like in this case, then the jump is smaller, weak. And if you continue, let's use green, then in this case this one is weaker. Okay, so that jump around the equivalence point pH gets smaller and smaller, and it makes it even difficult to detect what the equivalence point is the weaker the acid becomes. Okay, the regions that we have here are similar to what we had in strong acids and bases. However, here I want to bring to your attention this region here, which is around the pKa of the acid. And yeah, that's still controlled by the acid and the conjugate base, but this is for a weak acid. We call this the buffer region. That is the area and the titration curve in which the acid will behave as a buffer system. Okay, and interesting enough, here when you are halfway through the equivalence point, well, guess what? Halfway through, you have that the concentration of the acid is equal to the concentration of the conjugate base, and the pH is equal to the pKa. So if the Ka is 10 to the minus 8, then for this one pKa is equal to 8. For this one 10 to the minus 4, pKa is equal to 4. Okay, so here you will locate the pKa's of those acids. So how do we apply this to a practical problem? So we have three solutions here. Each one of them is an acid. You have the same concentration, but you have different pKa's. So let's start by ranking these acids as the from stronger to weakest. Okay, so if you remember, smaller pKa means stronger acid. Okay, so here we have the smallest is 4.20. Okay, that means that's the stronger acid. This is weaker and this is the weakest. All right, so but we are looking at the equivalence point, and at the equivalence point it's not the acid who is controlling the pH, is the conjugate base, right? So once we have this acid ranks from stronger to weakest, then one of the things that we need to do now is, well, based on that, which one is the strongest base, right? So in that regard, the strongest acid means you have the weakest base, and the weakest acid means you have the strongest base. Okay, therefore the weakest acid means this is the strongest base, and here for the strongest acid this is the weakest base. Now if we want to determine what the pH is, well, at the equivalence point the strongest base will give you the highest pH and the weakest base will give you the lowest pH. Okay, so if we want to determine now, well, if you want to assign your answers here, the lowest pH here, B will give you the lowest pH and C will give you the highest pH. Okay, now if you are calculating the pH at different points in the titration curve, well, the protocol is different now because you have to play with acid-base equilibrium. Okay, in this case we have formic acid, and for formic acid we have the Ka, and the first question is, what is the pH when you don't have any of the base? Okay, so let's work on that one first. So if you have that, okay, so you have 40 milliliters of 0.5 molar formic acid. So the concentration of the acid, concentration of HA is equal to 0.5 and Ka is equal to 1.8 10 to the negative 4. Therefore what we are calculating here is Ka equals x squared over 0.5, which means x is the square root of 0.5 times 1.8 10 to the negative 4. Okay, and this is equal to 949 10 to the negative 3. This is equal to our concentration of H+. Okay, we are just calculating the pH of a weak acid solution. All right, with you haven't added anything, so that's the concentration of H+. Therefore our pH is going to be minus log of 949 10 to the negative 3 and this is equal to 202. Okay, so before you add any sodium hydroxide, then that is going to be the pH. At the equivalence point, halfway through the equivalence point, there at that point the concentration of your acid is equal to the concentration of A minus. Okay, if it's halfway through the equivalence point, you have added half of it what's required to react with the acid. Therefore, at that point, you have consumed half of your acid, which means you have the other half of the acid is present as the salt. So at that point, the concentrations are equal. If we use pH equal pKa plus logarithm of A minus over HA, well, this ratio here is 1, which makes the whole thing 0. Logarithm of 1 is 0. Therefore, pH is equal to pKa, and pKa is equal to minus logarithm of 1.8 10 to the negative 4. And this is equal to 374. Okay, halfway through the equivalence point, the pH is 374. Now, at the equivalence point, all your acid is A minus now. However, we cannot assume that A minus is equal to 0.500 molar. So this is incorrect. Why? Because you have added some sodium hydroxide. Okay, you have to add some volume of sodium hydroxide. Okay, so if you want to do this formally, we can do the calculation. Okay, so how much you added? Well, the concentrations are similar. Not similar, the concentrations are the same, so you have to add 40 milliliters of sodium hydroxide to reach equivalence. Okay, so the same volume, if you have the same concentration, you need the same volume to provide the same number of moles. So your final volume here is actually 80 milliliters, but you need to calculate how many moles of the formic acid you had to begin with, right? So initially you had 0.040 liters of the acid times 0.5 moles per liter. Okay, and this is 0.02, right? So now your concentration of A minus is equal to 0.02 divided by 0.080, and this is equal to 0.250 molar. Okay, this is your concentration now. This is the concentration of A minus. Okay, since we are looking at the equilibrium of the conjugate base, then now we need Kb, and Kb is equal to 10 to the negative 14 divided by our Ka, which is 1.8 10 to the negative 4, and this is equal to 5.6 10 to the negative 11. Okay, so now what we do with this? Well, you have to remember that Kb is equal to x squared, in this particular case now divided by 0.25, which means x is going to be the square root of 0.25 times 5.6 10 to the negative 11. So x is equal to 374 10 to the negative 6. This is the concentration of OH minus, because we are working with a base equilibrium now. And the POH is equal to the minus log of 374 10 to the negative 6. And this is equal to 543. Therefore your pH is equal to 14 minus 543, and this is 855. Okay, so at the equivalence point the pH is equal to 857, which is a basic pH. Remember, at the equivalence point you have the conjugate base. The conjugate base will behave as a base, therefore you will end up with a basic pH. You will not be at neutrality. Now to calculate the pH past the equivalence point after you add 2 milliliters of the sodium hydroxide, well, pretty much at that point the sodium hydroxide is controlling the pH. The acid, the buffer, is already gone, it's been destroyed because you have consumed all of the acid from that buffer. You only have, at that point you only have the conjugate base, and if you continue adding base like sodium hydroxide, well, there is nothing that the buffer can do to avoid the change in pH. So the sodium hydroxide will overpower the conjugate base and then will be controlling the pH. So pretty much the pH will be whatever sodium hydroxide ions comes in these 2 milliliters of sodium hydroxide. So we can actually use the dilution equation. But remember that to get to the equivalence point you had to add 40 milliliters of the sodium hydroxide. So it's 2 milliliters after you have added those 40 milliliters. So your final volume is going to be your 80 milliliters that you had at the equivalence point plus the 2 milliliters extra that you are adding after reaching the equivalence point. So your final volume is actually 82 milliliters. Okay, so now to calculate the concentration of hydroxide at that point, okay, the only hydroxide that you will have in solution are the ones coming in those 2 milliliters, because the previous 40 have been already consumed. So we can actually use the dilution equation. So we have 2 milliliters times 0.5 molar divided by 82, because that's your final volume, and this is equal to 0.0122 molar. Okay, remember this is hydroxide. Therefore your pOH is going to be equal to minus logarithm of 0.0122, and this is equal to 1.91, and your pH is going to be 14 minus 191, and this is equal to 12.09. Okay, so past the equivalence point, once you added 2 milliliters of sodium hydroxide, then you end up with a pH of 12.09. And just look that you are jumping from 857 to 12.09, so you have almost 4 units of pH jump there. Okay, after you have destroyed the buffer. Now if you're using a base, well, there is again similar to what you saw before, except that the pH is going to be basic, not acidic, because you're starting with a base. Okay, the equivalence point is also acidic. Remember, at the equivalence point you have consumed all of the base, and then you have the conjugate acid, and it will behave as such. So it will increase the concentration of H plus in solution, and you end up with an acid pH. Okay, so this is how the curve look like. Okay, pretty much the same as with acids. You have a small jump when you start. Okay, and this region here, it's going to be the buffer region for the base, and the value that you have halfway through, that is going to be the pKb. Okay, you are starting with a base, so that is the region in which the base, the conjugate base acid pair will control the pH. Okay, the rest of the things also apply for this curve, in terms of the stronger the base or the weaker the base, the less the less abrupt the change around the let's put it this way, weaker base, less abrupt change at equivalence. Okay, so but how do we treat this problem? Pretty much exactly the same as we've done before. Okay, in this case we are starting with ammonia. And well, what is the concentration of ammonia is 0.150, and since you haven't added any of the acid yet, then the only thing that we have to do here is Kb is equal to x squared divided by the initial concentration, which is 0.15, which means x is equal to the square root of 0.15 times Kb, which is 1.8 10 to the negative 5. And this is equal to 164 10 to the negative 3. Now, you have to remember, this is concentration of OH minus, because you are working with a base. Okay? So the POH is the minus log of 164 10 to the negative 3, and this is equal to 278. Now you can calculate pH. pH is 14 minus 278 equals to 1122. So at the beginning, the pH of the solution is 1122. Now, halfway through the equivalence point, at that point, the concentration of NH3 is equal to the concentration of NH4 plus. Okay? But since we are working with a buffer at this point, then we need to see this from the point of view of the acid. So we need to calculate Ka. And Ka is Kw divided by Kb, which is 10 to the negative 14 divided by Kb, 1.8 10 to the negative 5. And this is equal to 549 10 to the negative 10. Okay? So if you calculate pKa here, then you obtain 926. And why do I do that? Because now pH is equal to pKa plus logarithm of A minus over HA. This is A minus, okay, and this is HA, just in case. But because the concentrations are equal, this whole term is 0, which means the pH is equal to 926. Okay, pH equals to pKa, 926. Now at the equivalence point, at equivalence, okay, all NH3 is now NH4 plus. Okay, so we already have the Ka here. All right, but we need to determine what the concentration is, because you started with 20 mLs, but you need to know how much HCl you needed to add. Okay, so let's calculate that. So you had 20 10 to the negative 3 liters, and the concentration is 0.50 moles of A minus per liter. The stoichiometry is 1 to 1, so you need 1 mole HCl per mole of A minus. and the concentration of your acid was 0.200. So you had 0.200 moles of HCl per liter. So we cancel all of these, and we end up having to add 0.050 liters. Okay, which means you added actually 50 milliliters. Okay, that means your final volume is 20 milliliters plus 15 milliliters equal 35, which is 0.035 liters. Okay, how much ammonia you have to begin with? You had 20 10 to the negative 3 liters times 0.150 moles per liter, and this is 0.0030 moles. So your new concentration of NH4 plus is equal to 0.0030 divided by 0.035, and this is equal to 0.0587 molar. Okay, so what do we do with this? So this is your concentration of your NH4 plus. You are at the equivalence point. The pH is controlled by NH4 plus. Okay, we have Ka. Ka is going to be x squared divided by 0.0857, which means x is equal to the the square root of 0.0857 times Ka, and Ka is 5.49 10 to the negative 10. And this is equal to 693 10 to the negative 6. Now this is concentration of H plus. Therefore your pH is equal to minus log of 693 10 to the negative 6, which is 516. Okay, so last but not least, the last case is when you have added 1.2 milliliters in excess of HCl. At that point, only the HCl is controlling the pH, and basically the only hydronium coming from HCl is the one contained here in 1.2. Since at equivalence your final volume is 35 milliliters, your final volume after added 1.2 milliliters, it's going to be 35 plus 1.2 equal 36.2 milliliters. So the concentration of your acid, which we can use again the dilution equation, is going to be 1.2 milliliters times the concentration of your acid, which is 0.200, divided by 36.2, and this is equal to 0.0066. Therefore your pH is equal to minus log of 0.0066, which is equal to 218. Alright, now a different story we have when you are titrating a diprotic acid. Why? Because even if you are having a titration reaction here, which is an acid-base reaction, well, the diprotic acid will react one proton at a time. The reaction will go to completion, but you will be consuming one proton at a time. And this is how it looks. Technically, you should be able to calculate anything that you need in this curve, but things to keep in mind. You have two equivalence points. Okay? Two equivalence points because you have a diprotic acid. Okay, and diprotic acid, right? So you have Ka1 and Ka2. So you have two inflection curves here. So you have buffer zone 1 and then you have buffer zone 2. One for Ka1 and one for Ka2. Okay, and this here halfway, this is your value for Ka1, and here again halfway on the second point, this is your Ka2. Okay, so technically, depending on what part you are in this equilibrium, you should be able to calculate any pH. Okay, would you have to do that in the exam? I don't think so, but don't quote me on that. Okay, so in review, if you are working with a weak acid strong base titration, things to remember: the pH at the equivalence point is basic, and that is because the conjugate base controls the pH at that point. Okay, there is a less abrupt pH change near the equivalent point, and sometimes if the acid is very weak, it makes it difficult to detect the equivalence point. Okay, if the acid is weaker and weaker, when the higher the initial pH of the titration, and sometimes it also means that the higher the pH at the equivalence point, because if the acid is weaker, then the conjugate base is stronger, and then it will favor the production of OH minus. Okay, things to remember here, because these are weak acids, halfway through the equivalence point, the pH is equal to the pKa of that acid that you're titrating. If, in the other hand, you are titrating a weak base, then again, it's similar to what you've seen before, except that the initial pH is basic. The equivalence point, the pH is acidic because the conjugate acid controls the pH. Okay, and at half the equivalence point, then the pKa of the conjugate acid is what the pH you're gonna have, not the pKb. Okay, remember, because you are working with you are working with pH. What you are plotting is pH, so pH depends on the concentration of H+, and if you are titrating a base, even if you are in that case and you have Kb, is the conjugate acid who is providing the H+, and that's why that value that you will see there, even starting with a base, that's going to be the pKa of the conjugate acid. Okay, so that's it.